Worked for one of the DOTs and found out that you can reduce 25% of the reinforcing bars for fracture if you put 0.5% fibers, because you have to offset the cost. They're not, like you said, they're not free. We don't use them to reduce the steel, but if you reduce the steel, you make it easier for them to be cast. You use them to increase the toughness, strength.
Instead of steel fiber, we can put polypropylene in the.
Yes, you can.
It's better or not?
No, it's not better.
Not better.
But it's okay.
Stress is decreased.
Yeah, steel fiber has.
Steel fiber stress increase.
Yes, and toughness.
Toughness.
Yes, sir.
The reference for the 0.5% steel fibers, was it to what? 0.5%
by volume of concrete. So
concrete, the whole concrete.
Yes, so it's 39 kilogram per cubic meter. Density of steel is 7.8. So 50% is almost 40 kilogram per cubic meter.
0.5 instead of cement or concrete?
Concrete.
I think cement.
No, it's not. I'm the professor. بالعفو, لا, 0.5% of the volume of the concrete.
In the laboratory, we can't put 0.5 instead of concrete. We can put 0.5 instead of cement.
Yeah, I understand.
It's very difficult.
No, I understand, but in fiber reinforcement, you always express it as percentage of the volume of the concrete.
Maybe adding, not instead of adding.
Well, yeah, you are adding. So like here.
Adding manually.
Adding, yes.
Yeah. Like it's 40 kilogram per cubic meter. It's like one sack of cement.
Fibers. Sorry, I can add something. With aspect ratio more than LRB, more than 50.
Yes, in this case it's 60. Yes.
Yes, minimum aspect ratio LRB.
Yes.
Greater than 50.
Yes. It's important. The L over D is very important. Yes. Sorry. Okay. Next. So the gearing is the same test as the slump flow, but you put a ring that has 16 rebars, and there's an opening here about 38 millimeters. So it's if you have an aggregate of 25, it's 1.5 times, and you measure the diameter at the ends. So if the diameter is low, that means the presence of rebars is really restricting the flow. And we call that passing ability. The passing ability is low. If the slump flow is very high and the gearing is very high, that means the passing ability is also high. I'm going to skip this next. Okay, so stability, I mentioned visual stability index 0, 1 is good. And I said if it's 1 doesn't mean that's very good, it's okay. You have to do more testing. So there's a test method, it's called the surface settlement test method. So we take a sample of concrete, 660 millimeter, in a tube of 20 centimeter. We cast the concrete, no consolidation, and we look at the settlement of the surface. It's like you saw that wall after 3.5 minutes. Next. So the surface settles, so there's a deformation of the surface, and then we monitor that with time. So for example, in the black, you have conventional concrete, 150 millimeter, vibrated, and you see that the settlement is fairly low, not black, in pink. This is expressed as a high percentage of the height, so 0.3% of the height. So 0.3% of the height is about 1.8 millimeters. The one on the very top in yellow, it's 0.42 water cement ratio without any viscosity modifier admixture. And you can see the settlement is 0.8. So by building viscosity, we mentioned viscosity, by using viscosity modifier admixtures or reducing the water to binder ratio, we can make the concrete more cohesive. And that's a very good test of stability. Better than bleeding, better than visual stability, it's a settlement test. Okay, let's go back to use of this beautiful material SCC for repair. Again, I showed you why it's used in repair, because you have areas that are very restricted. This thickness here is usually 50 centimeter, 5 centimeter, 50 millimeter, 75 millimeter. You want always to have some space behind the rebars to anchor the repair. And it's going to be restricted, and you can be repairing a wall that is 7 meters in height. Again, you drop it, you put a trimming or a pipeline, and you pull it slowly, and you fill the formwork.
Oh.
Next. So this photo here is in the year 2000. This was one of the first repairs of SCC anywhere. So this is a retaining wall in downtown Montreal, and a lot of corrosion. And they designed the architects designed a bell shape, so very small at the top, very wide at the bottom, very difficult to put a vibrator and vibrate the concrete. So they decided to use SCC, and here you have the flow properties. So the slump flow is very high. It's uniform. VSI is 0. The gearing has to be at least 550. The surface settlement maximum 0.5%, and the 56-day compressive strengths, you want it to be more than 35 MPa, but less than 60 MPa. You don't see specification less than. The reason for that, if you make it very high strength, it cracks. And when you do repair, there's a lot of restraint shrinkage. So you put a concrete that is going to shrink, and the substrate that is a 75-year-old concrete, there's no shrinkage. And you're putting a thickness of, let's say 75, 100 millimeter, it's going to shrink, and it's going to be restrained from the sub-base. So you don't want it to be very rigid. It's a way of controlling elastic modulus of the concrete. Next.
But sorry.
It's a way of controlling the elastic modulus.
Sorry for interrupt. But I think you can over plastic shrinkage by adding steel fiber or polypropylene fiber.
Oh, so this is not plastic shrinkage.
Yes.
Restraint shrinkage.
Restraint shrinkage.
Restraint
You
You can.
shrinkage
You're right.
by adding steel fiber.
You're
or
right.
polypropylene.
You're right. So the next job, after this, 2 years later, we tried polypropylene fibers. Synthetic fibers at 0.25% by volume of the concrete. Next. So these are results from 40 repair sections that were done. The slump flow of the concrete varied between 620 and 720. After 60 minutes, we lost less than 50 mm of slump flow. The surface settlement was always less than 5%. And these fresh air content, 5 to 8%. Next. Mechanical properties. After 1 day, we had 5 MPa, which is important to be able to remove the formwork. But you don't want 20. You want 5, 7, 10 maximum. And you can see the strengths. Again, the strengths is not important here. What is important is the workability and durability. You're going faster than me. The RCPT, so this is a coolant value for corrosion resistance.
But Master, we need also strength in bridges. We need the high strength.
Of course.
Okay, also workability, strength, workability, also toughness and ductility, something like that.
Of course, you can get all of those.
Maximum I see here 30 megapascal.
Because yes, it's on purpose low. What's important here is that if you make it very high strength, you don't need it because the substrate is not high strength. You need a repair material in this case for durability of the repair itself.
I mean that we use it in bridges, that's right?
This one is for
deck of bridges.
No, this one is repair for infrastructure, for repair of piers, of walls, of retaining walls, of girders. But if you want to use this for construction, vertical construction,
but we can reach 40. We can reach in this case for concrete 40 megapascal for concrete.
yeah. So I mean,
40,
you can,
45 also like this. Not high strength concrete.
in this next design, the water to binder ratio is 0.42. Yes, but you can reduce it to 0.3 and get strength.
Yeah.
I mean,
if you put fiber, easy reach 40, 45 like this. Steel fiber or polypropylene fiber.
So fibers don't increase compressive strength and flexural strength.
Steel fiber increase.
Very little.
Little, yes.
We
have five like this, 5, 6, 10,
yeah,
10 maximum like this.
Right. It increases performance after cracking. So until cracking, there's no, because the fibers are inactive. They get activated once you have deformation and cracking. They increase the load carrying capacity, the toughness. But you can make 80, 90 megapascal concrete that is SCC, and it's been made. You just have lower water binder ratio.
You put here also fly ash.
Yes.
5%.
I'm not going to tell you 5% or 25%. You have to work with the materials. Burj Khalifa, for example, is a C60 concrete. The Kingdom Tower in Jeddah is C90 concrete.
By the way,
it's all SCC.
Iconic tower here, they used spike compressive strength 80 megapascal.
Yeah.
An iconic tower. And Tahya Nasr Bridge, the strength was 100 megapascal.
Wow.
And by the way, I got 127 megapascal.
High strength concrete.
High strength, of course. Yes.
Fly ash. Not fly ash, silica fume.
Silica fume. Yeah, silica fume. Yeah.
In this case.
Like 6-7% silica fume, maybe. Yeah. When you high strength concrete, it's much easier with some silica fume.
You should decrease the water bind ratio.
Of course.
Water cement bind.
0.4 maybe water cement ratio.
0.18 or 0.19 water cement ratio.
So that's UHPC.
And ultra high performance.
Yeah, ultra high performance concrete, 150 MPa. I like it. You guys have high technology.
Yes.
2% fibers. Yes.
Maybe more.
Concrete next design in bridges in Gulf. In Kuwait, we use 5% microsilica plus 13% GGBS.
GGBS. Yeah, 5% silica fume, GGBS 30. That's a very nice combination. When you combine silica fume, low percentage, 5% with 30% GGBS or 30% fly ash, you are getting good backing density of the powder. And you are reducing the space that needs to be filled with hydration products. So you get low porosity, high strength, high durability. Thank you. Next. All right, so we came back after 1 year, and then these repair sections are made in 4 meters. And then typically, we found that there's one crack every 4 meters, about crack spacing is about 2.7 meters. The crack opening is limited to 0.2 millimeter, very small. Now, when the contractor was using conventional concrete, not SCC, conventional concrete, the crack widths were larger, and there were about 3 to 4 cracks per section. So the concrete that was developed, obviously, is not only filling the formwork, but also developing lower restraint shrinkage, higher strengths, less cracking. And as a result, it's going to be more durable. Okay. Next. All right. How are we doing? Okay. Fine. Okay. So let's go underwater now. Next. This is the Champlain Bridge in Montreal. It was just replaced recently after almost. It was constructed in 1960, and it was replaced about 5 years ago. So almost 6 years of service. It's the most traveled bridge in Canada. It's a 3-lane bridge on each direction, and there's 40 of these piers. And you can see there's a lot of cracking. Weber will be very happy to send some repair materials, mortars and epoxy and all this good stuff. So what they do every year, they do 4 piers. They repair them after 10 years, they come back and then do another 4, 10 years they do it. So there's 40 of them, they do 4 per year.
Maybe the reason for these cracks is maybe rebars.
Yeah,
corrosion of rebars.
There's corrosion of rebars, there's issues with freezing and sewing, there's issues with alkali silica reactivity. There's also some issues with the shrinkage and thermal shrinkage.
So if we use, instead of steel, normal steel, we can use TFR carbon for reinforced steel
Yes.
instead of normal steel.
GFRP, yes.
Not GFRP
Glass.
suitable for deck,
Okay.
but for column we can
Columns.
use carbon.
Carbon, yeah. Well, this bridge was constructed in 1960. They did not have that technology.
All
Yes. Next.
Is there a role for the corrosion inhibitors in this type of concrete?
I mean, if you have to do this now, you would use some silica fume, you would use some STMs, proper mix design, and then corrosion inhibitor, yes. When it comes to, in structural design, when we do structural design, we always do something redundant. We don't only depend on one mechanism of failure. If there's one mechanism of failure, something else kicks in and prevents it from failing. When we do mixed design for concrete, we should also use multiple mechanisms of, in this case, corrosion inhibitor versus thick cover versus proper curing. Yes, sir.
If we go back to the last slide, notably near the surface of the water, you have the worst scenarios because of the fluctuations.
That's right. That's
so is it worth it to use these all over the whole structure, or just maybe when you come to this level you put different concrete, and would that be a strategy for?
Yeah, so you're right. Normally, if you look at marine structure, the surf zone, where you have a tidal zone up and down and splash, that's the one that has most amount of damage because of wetting and drying and corrosion. So this is where you need the most of the ribbon. Submerged zone is less important, the atmospheric zone. So you design for the worst case. In this case, it's the St. Lawrence River. There's no salt. But the water line has some abrasion from waterborne debris, sand, and ice abrasion. So, but the cracks that you see there are mostly corrosion and alkali silica activity. I want to take you underwater next. So when this bridge was constructed, you have the pier that is properly reinforced, that the footing is sitting on soil and it looks like a bell shape. It's totally unreinforced, so there's no reinforcement here. It's unreinforced concrete. There's only reinforcement at the bottom to spread the load. This was cast during the summer, mass concrete, and it cracked. They did not control the temperature. Next. So the cracks that you see are vertical, horizontal, radial, and they determine that those are dormant cracks. So that means if you inject them, they're not going to continue moving. So you can inject them. And the reason they repair it is to keep it integrated so it doesn't disintegrate. And also you don't want a block or big concrete in the shipping lanes. There's a lot of boating and shipping and leisure boats. Next. So this is a close view of the cracks. Cracks can be a couple of millimeter up to 10 millimeter in thickness. They're very large cracks. Next. So they took some cores, 6.7 meters, and they determined in situ the strength is not bad. After 50 years, the strength is not bad, but there's a lot of visual cracks. The concrete was not air entrained. It was at the time the water reducing admixture that entrained a little bit of air, but the air contact is not adequate. So you want this number here to be 200, 250. It's 500, 700. Your air bubbles are too large, and that's why in the pier you have damage from freezing and thawing. And they found out that they have some alkali silica reactivity. Next. So a typical repair would be to send a diver underwater. So there's the caisson here to reduce the current. Next. And then they do injection. This is showing you what they do above water. Next. Okay. let me know. So as this guy is injecting, is thinking of the physics, let's go with physics. The velocity, maximum velocity of penetration of the grout is dependent of 1 over mu. Mu is the viscosity. So that's why you have to have low viscosity. If you have low viscosity, the penetration depth, not depth, the speed is going to be higher. And the other parameter that is important here is tau zero. Tau zero is the yield stress, and the lengths of penetration, the depths of penetration is going to be dependent of 1 over tau zero. So if you reduce yield stress, you make your grout very flowable, it's going to penetrate deeper. If you make it less viscous, it's going to go faster. So I'm sure that the repairman is thinking about that as he's injecting. But right now he's injecting epoxy, and of course it has to be epoxy that is going to set underwater, which is special epoxy. Next.
Is it fast setting?
Fast setting. So this is underwater. What they would do, they would use a high-speed water jetting or a steel brush, and they would remove all that marine deposit, expose the cracks. Next. And then you have to inject it. So our approach for the bridge authority is like, we would like to use some cement-based materials instead of epoxy. And would like to see if cement-based materials can be effective in injecting those cracks. So when you do cement-based materials, no, this is fine, thank you. I'll tell you.
I'm sorry, this is the end of the day.
That's okay. So when you put cement grout, this is only cement and water. With time, it's going to segregate. The cement is going to settle and the water is going to. You don't want that in your crack. You want in your crack something that is homogeneous until it sets. So this is a homogeneous grout, and you put some VMA, for example, viscosity modifier. Next. So we were working quite a bit in underwater grouting, and we took some blocks of concrete, we put some cores, and then we put some rebars and injected them with above water, underwater, with cement grout. And let it harden, and then you do pull out. Next. So on the vertical axis, you have the ratio of the maximum load of those anchor bars that are pulled, they were cast underwater versus those that were cast above water in the dry. So the ratio is 1, that means underwater, above water is the same. You want that ratio to be as high as possible. And we can see here for cement paste, this is cement paste, okay, cement and water. For cement paste that is very flowable, 125 mm, if you reduce your washout mass loss, so how much washout, if you drop this grout in water, you lose some mass because of the dilution. If you make your grout viscous, use anti-washout admixture, use some silica fuel, you can reduce that, and by reducing that, you are increasing the performance.
But why you did pull-out test? What is the benefits of pull-out test in this case?
So this was another project. We were doing underwater repair grouting for underwater repair anchors, but I'm showing you the behavior of the material. Pull-out is a very good characterization of the bond between the steel and the grout. If the quality of the grout is low, you're going to feel it, not in compressive strength, but in pull-out. So it's an indication. Next. You want also your grout to be able to penetrate very small cracks. And one test we found out is from the French standards. It's called the sand penetration column. So you have a column over here of sand. It's a graduated column, white sand, and you put grout here, and under pressure, you grout it, and you see the depth of penetration in this sand column. Sand column is probably 30 centimeters in height. In some cases, it will penetrate all the way because the grout is the cement particles are fine, the grout is flowable, and sometimes it will block. You don't want it to block, you want it to penetrate all the way. It's a standard test. Next. So we use the materials, silica fume 8%.
Sorry.
Yes, sir.
You said sometimes the mortar block.
Yes.
Why?
It blocks because the cement particles are big enough that they don't penetrate the space between the sand particles. So the column, the sand column test, the type of sand that you use can reflect the crack open.
But I think from the first I should use fine sand, a fine particle.
Yes, fine
From
particles.
the part.
Yes,
The start.
and that's exactly what we had to do. I'll show you. Using a microfine cement. So we tried to use Portland cement, type 1 cement, and silica fume. We tried also to use microfine cement, and the microfine cement is 75% grounder GGBS. It's very, very fine GGBS. You see the D50, the 3.5 micron. If you take a D50 of Portland cement, it's like 14 micron. So it's much finer. It's going to penetrate smaller cracks. We use naphthalene-based superplasticizer, not polycarboxylate, and we use whale and gum as anti-washout admixture. Next. So we compared two grouts. We compared the cement-based grouts to moisture-insensitive epoxy grouts that has been used. You have the mechanical properties, the tensile property, elongation. Of course, the advantage about epoxy grouts, they have a lot of tendency to elongate without cracking. Next. So in terms of cement-based grouts, we have here 4 mixtures. Control, you see the water-cement ratios, the mini slump. The sand column is fast, blocked. Anti-washout, number 1, anti-washout, number 2. And the last column is what I'd like to draw your attention, the use of microfine cement. It was the first time we used this microfine cement. So the water-cement ratio is 0.6, and the mini slump is very, very high. Strength is not very important, but you have okay strengths. No problem. But what really was really good is that the microfine cement, which is red, is almost Newtonian. So with the cement, the top 3 figures, you see that the viscosity is high at low shear rates. That means if you're injecting, with the injection, initially there's high shear rate. Velocity is very high. But if you are 30, 60 centimeter from the surface, the shear rate becomes very low. Speed is low, and the viscosity becomes high. It blocks. So you might be able only to penetrate 30 centimeter. But with microfine cement, viscosity was always lower, and it did not depend so much on the shear rate. Now we felt that this is very important, being very fine and being low viscosity and not shear thickening is going to really help us on the performance. Next.
Sorry for interrupt, but this is, I think there is a contradiction between this, you said that, and the equation you showed us, the viscosity was in the denominator.
Yeah, so you want to reduce the viscosity. V max is equal 1 over viscosity.
Yes, the viscosity in the denominator.
Yeah.
So when I decrease it, the velocities increase. Okay, but you said that, I think, as I focused with you, said
You want the viscosity to be low. Yeah.
Low, and also the speed, I think the viscosity is low, and the speed.
It's the shear rate.
Yes.
The shear rate is dVdx.
Yes.
Maximum depth for injection.
Yeah.
30 centimeter like this or what?
Oh, in this case, it was an order of meters.
What?
Meters.
1
meters. Yeah. And the whole block is 10 meters. So yes. Next. Okay, so typical results. We did a lot of. So again, they gave you 2 peers and say do them using epoxy and two piers using.
What is the total length for the pier, for the footing or the column? Maybe 3 meters or like this?
10 meters.
10 meters, okay. If you said that 1 meter maximum injection,
Yes.
what about
Inside it's probably not cracked, it's outside, yeah. Cracking usually mass concrete is on the
The
outside.
first picture we see that like, it is like shrinkage cracks.
Yeah, those are thermal shrinkage. They are shrinkage crack, but also thermal shrinkage because they cast it as mass concrete, one block, and it cooled off too quickly. They did not control the gradient of temperature, and it cracked on the outside.
I want to say that maybe the reason for these cracks, maybe there is no shrinkage reinforcement mesh.
Oh, there isn't any. You're right. There's zero. No reinforcement. Zero.
It is not good.
It's just concrete block.
It is not good. We have to put after 2 meter or like this 1 meter 0.5.
You're right.
We have to put shrinkage mesh
You're right.
reinforcement. So the first picture we see that shrinkage cracks.
Yes.
This is the reason, the main reason for without we didn't put shrinkage reinforcement.
This is 1960 technology, my friend. 1960. So we had a technician that used to work on this job, and he said the structural engineer, he was a French person, and his name was Mr. Pouce. In French, pouce means inch. 1 inch is un pouce. And he said the concrete should not be more than 1 inch, because if you add a slump, that means you're adding water.
But I expect that there is
Let me-
in the middle also.
There is cracks everywhere. So when they did the mock-up, the first mock-up, and they cast it was a slump of 1 inch, you can see through it. You can put your hand in it. Because it was, yeah. Yeah, I mean, this was 1960 technology. They did not do it right. But you're right, you have to have at minimum shrinkage, minimum thermal and shrinkage steel, minimum, and there was nothing here. Okay. No, please go back. Okay, this is very important. So these are the properties of the cement paste. Again, it was microfine cement, epoxies. Setting time did not set for 30 hours. It's microfine cement, lots of slag. Doesn't bother us. It's important to set and harden as long as it's stable. Next. So the epoxy resin, you can see that the injection points, there was a manometer on the barge, on the river, 1.5 megapascal pressure, and at the injection point it was 1.5. The refusal pressure was to maintain that pressure for 2 minutes, and there's no more intake. That means it's not getting inside the concrete anymore. You stop injection. The injection was carried at 25 degrees plus or minus. This is for the epoxy. Next, for the microfine cement, the injection pressure was a lot less. Instead of 1.5 megapascal, it was 0.35. And this is very important because you have a bridge over it, and this is the unreinforced. If you have a lot of pressure, you can elevate. So 0.35 megapascal, and again, refusal was 2 hours without intake. Next. And this is very important. You were asking me about the lengths and stuff. So in both bridges, they repaired 600 linear meter of cracks, 660, 650, 640. So linear meter of cracks is the same, but the volume of grout that was injected per linear meter of crack was 3 times more. On the cement, the microfine cement, you injected 1,250 liters versus epoxy 460 liters. So the intake was a lot more, 3 times more, which means that you penetrated more and you were able to have better repair.
600 millimeter or what?
600 liters.
Liters?
No, 600, sorry, meters. Linear meters. So again, you have a block of 10 meters, around it, 600. And then we took some course and looked at the repair. You see, this is a microfine cement. Next. We also did some pull-outs to test the bond strengths between the epoxy and the concrete, or the microfine cement grout and the concrete. Next. And you can see in terms of mean bond strengths, the values vary a lot, but you get similar values more or less between the epoxy and the microfine cement. Minimum values, maximum values, and this is visual inspection about the filling capacity. Around the crack, how much of the cracks are filled in the core. Next. One thing we noticed when we put it under a microscope, the epoxy has a filler. So epoxies, even the epoxy resins, they're not just pure polymers, they have some fillers. Limestone, small fillers. And on one side here, the white is a crack, concrete, existing concrete, and in between, you have the epoxy. And then you get to a point where the crack width is very small. And if you have some fillers that are blocking, then you don't have any more penetration. That's why it's very important to control the maximum size of any inclusion when you are grouting, otherwise you're going to block. Next. So we had a colleague that was working in non-destructive testing, and we asked him to help us do some non-destructive testing underwater with divers. So basically, again, this is a pier that is 10 millimeter in diameter, 3.5 meters in height. So they put some geofoams on one side and geofoams on the other side. And the diver with a big hammer, he hits one of them, and they listen to the time that is needed to reach each of those geofoams. They do some Fourier analysis, and they determine the elastic modulus, dynamic elastic modulus. Depends on the speed of propagation of pressure waves, P waves. Next. So you can construct that as a contour diagram, and the colors corresponds to the speed of propagation. So speed of propagation of 4.5 kilometers. Try to remember kilometers per second, I think. Or is it per minute? I think kilometers per second. Yeah. That means the quality is excellent. And then the blue is 4.5, 4 to 4.5 good, yellow good, orange is deteriorated, red is poor. So here you see that the color, and by the way, this is the side where the river flows. So the side where the river flows, you have more abrasion and you have more damage. Next. So this was before the repair, and look at the color now, it's going to be mostly blue. Next. This is after the repair. So you see after the repair, most of the concrete now has dark blue, which is 4.5 kilometers per second. Again, it reflects the elastic modulus. It reflects that you have done a good job on the repair. Next.
It's a perfect repair.
It's a perfect repair. MashaAllah. Okay. I don't know how much time you want to spend more. I was going to talk to you about the repair of these water lines. So again, this is downtown Montreal, and then they have the water lines, the pressure pipes. And then because of the penetration of salt from the pavement, eventually they corrode and they snap, and then you have a break of water lines, and for a long time people don't have water. So from time to time you have to repair them.
Yes, Doctor. In previous case, if we use now repair, we can use CF laminas for carbon fiber laminas.
Yes.
Instead of injection.
Oh.
It is okay now or not?
It's a little bit difficult to do it underwater. Yeah. You know, the laminas is basically confined. It's like putting stirrups around the column. is external confinement.
If it is above water, not
I mean, you could, there's a lot of work repair using strips.
can
of-
solve the problem for cracks, which we see.
Yeah, it works well.
It's okay. But
Yes, sir.
what about cost?
They're not very expensive. I mean, you don't have to jacket the whole thing. Sometimes you can just put, like you said, laminates, strips,
Yes.
to repair shear cracks. It's basically structural retrofit.
Which one is more cost? Injection or laminates?
I cannot tell you. You have to do analysis.
وانا اسف ليا وجهه نظر في الموضوع. ده ترميم ده تدعيم
تدعيم من حالة الكربون.
بالظبط.
لامينات.
لكن مفيش غنى عن عمليه الريبير او الترميم نفسها او الانجكشن نفسها لانها بتعالج جسم الخرسانه، بتعالجه من الاساس من الداخل. عمليه الكربون فايبر هي مجرد تدعيم خارجي، تمام؟ زيه زي قميص خرساني لو بنتكلم بالبلدي. فانا دايما بختلف ما بين سترينثنينج او تدعيم وريبير. ترميم ريبير انا بنقذ الخرسانه، تمام، بلحقها
والاسترنس بيبقى زي ما هو تقريبا.
بالظبط. لكن
الاسترنس ممكن الاسترنس يزيد في حالة اللامينات.
التدعيم بالظبط. شكرا.
He didn't give us any cup of
Only
any point. It's any drop.
Sorry.
No, it's there. You can help yourself.
Lecture is very interesting.
Thank you.
Could you please go?
All right. So let's continue. Please, next slide. Okay. So the idea is that if you have a break of one of those vanes, you have the original one, you insert a smaller one, and then you have to eject this annular space with the material that is really extremely complex material. I'm going to show you examples of it. So you have the diameter 1.8 meter, and you have the corrugated steel, if that's what it is, or other type of materials that is smaller in diameter. So the difference between them divided by 2 is the space that you have to penetrate. So that's about 7.5 centimeter on the average on each side. And you have to inject that. So water pipes are at 150 psi. And again, if there's any corrosion blow up, you have basically a geyser from the city street. Next, please. So the space that needs to be filled varies between 50 to 80 millimeter. And the spacing between the injection point are the maintenance halls on the street level. And they are spaced usually about 100 meters. So you have to go from one maintenance hall on the city street all the way to Bunya al-Qadiyah, all the way 100 meters. You don't consolidate, you don't vibrate. Self-leveling, self-consolidating, very small space. Casting duration can be 2 to 3 hours, and the rate of filling has to be slow, otherwise you trap air, 50 meters per hour. So filling that column can take at least 2 hours, which means you have the material to have properties that don't change for at least 2 hours. Next. And then you wanted this mortar or this grout to be very stable, very flow, but very stable. And in this case, you don't have good stability. At the top, at the crown, you have settlement. You have bleeding, you have settlement, right? You want it to fill completely. Next. So we worked with the city of Montreal, and we worked with, I don't know, 5, 6 material producers, competitors, that they gave us different products. And we determined, okay, to write some specifications, what's the best knowledge around the table? And we came up with, we would like to have a material for repair that has a flow retention of at least 3 hours. Passing ability retention for at least 3 hours. Resistance to bleeding and settlement, so we don't have that separation. It does not change its rheological properties. Yield stress, classic viscosity of 3 hours. Compressive strengths, development, We follow it, but it's not very important. It's a filling material. You need some strength, but that's not. Recommended testing program, and what are the quality control test methods that you can specify and control that material. Next. So we worked with ready-mix producers. I'm just calling them here A1, A2, B1. 3 competitors. They're all friends. They're all partners. They are doing this to be able to qualify their materials to be specified by the municipality. Again, this could be municipality of Giza, and they're going to put in their specs products A, B, C can be used because they already passed the test. And then we had different producers had pre-packaged products, and then one producer that has a ready-mix concrete supply. So we invited everyone to submit their products, and we tested them in a very rigorous manner, and we gave them the results. So when you give them the results, you get an envelope, and you say your product is product C. You only know which product is yours. And after that, we gave them another chance to redesign or modify their product, and we tested it again. Okay? Next. So some materials, all the producers came to our lab. They brought their equipment, they brought their technical staff, and they prepared their own materials according to their specifications. We only tested them. So some producers use mortar mixers, others use ready-mix mortars, others were ready-mix trucks. So the test methods, we cast some cubes, 50 millimeter cubes. They were demolded either at 1 day or at 7 days. 7 days when they were confined. So you know these materials, if you're going to eliminate settlements, often they're going to have some expansive agents or shrinkage compensating agents, and you have to confine them. You cannot, if it's unconfined, you have a lot of expansion, and that reduces strength. You have to confine it because you are in a confined environment. Next. We did many test methods. I'm going to present most of them, but not all of them. Next. So very simple test method, the slump, the mini slump. So this is not a slump cone, it's a mini slump. You have the dimensions. Next. We also did the passing ability using either the standard ASTM test C939. The opening here is 12.5 millimeter. You measure the flow time. Or a larger one for mortars, V-funnel. Next. We also looked at bleeding, and then we have the graduated cylinders that allow you to look at the bleed water accumulation on the top. But we also did pressure bleeding. That means we're trying to have bleeding under pressure to separate the water from the mortar. And we wanted to have, go back please. We wanted to have minimum amount of bleeding of less than 0.3% of the height after 3 hours. So a material that is very stable. Next. So for fluidity, we wanted something to be obviously SCC consistency, self-leveling, self-consolidating, no blockage, no segregation, retention of flowability for 3 hours. 2 is passing ability. Setting time, we measure setting time. And we notice the setting time is between 5 hours and 24 hours. Next. I'm going to skip mixing. Mixing is standard procedure according to the specification of the producers. Next. Next. So these are all the materials. We are measuring here the mini slump. Again, mini slump is a small cone. You lift it without any consolidation, you measure the diameter. We're interested in what happens initially all the way to 3 hours, 3.5 hours. And the specification was to maintain fluidity for at least 2 hours and minimize anything above 50 and at 3 hours. So you can see the materials that are produced have different fluidity, but all of them have pretty good fluidity retention. Next. We also, instead of using a smoke cone, we said, okay, sometimes on the job site we don't have a smoke cone, let's use a concrete cone, big cone. So we found out that there's a good relationship between the small cone and the big cone. This is, so you're talking about 1 meter, you're talking about this. Next. We also wanted to look at flow time, gives us an idea of viscosity. Again, retention of viscosity is quite good. Next. Next. And then bleeding, all of them gave us 0 bleeding. They're all very stable. Next. And next. But when you put them under pressure bleeding, the prepackaged materials had the best stability, the ready mix was less stable, and the neat cement paste was the least stable. Prepackaged materials were better. Next. I'm almost done. Setting time, initial setting, final setting. Again, 8 hours, final setting anywhere between 9 hours, 24 hours. Next. Compressive strengths, we wanted to have compressive strengths of 20 megapascal at 28 days, and you can see everything is okay. There's no red flag at all. Next. Next, shrinkage. So let's keep going. Okay, no, can you go back, please? Okay, so the fluidity, after having tested all the products twice, we decided the mini slump should be at least 180 millimeter. The mini slump flow after 3 hours should be at least 150 millimeter. And next. And the passing ability, V funnel should be 3 to 8 seconds. And the flow time, 20. And then we said, these are the test methods for mixture design, and these are the test methods for acceptance testing on the job site. Acceptance, obviously, you're not going to do all the test methods. But when you develop your mix, you want to do all of them. Next. Next. Okay. So finally, we decided to do a study on one of the materials, and it was a mortar that was self-consolidated mortar that was mixed in a ready-mixed concrete truck. So sand and water, you could see the properties. The slump flow was 710, the air content, static bleeding, 000, expansion, compressive strengths, adequate. Next. Of course, the most important test is the penetration. So for the penetration, you can see the annular spacings at the top 80 millimeter. It was inserted as far as possible, and then they started injecting and bringing it back, filling that annular spacing. Next. And then when they were finished, so this is the slump flow. Again, it's a mortar, very stable and very flowable, and a total of 50 cubic meter of concrete was used to fill that annular spacing. The grouting was 87 meters in length, and the trial was very successful. This is my last slide. So, as a result, everybody, competitors, got to have a test method to be able to develop their mixtures, and then since they met all these specifications, the municipality, which is in this case the city of Montreal, said these products, this formulation can be used on any one of our jobs. So you develop performance-based specifications that are related to specific test methods. So I hope that I gave you an idea about some of the repair and rehabilitation products that can be used for repair of infrastructure or repair of bridges or reconstruction, like the fiber reinforced concrete. And I thank you for being here.